Okay, let's get started. Good afternoon, everyone. Welcome to the SYE Colloquium Series. Today, we are very happy to invite Dr. Iris Rivero to give us a talk. Dr. Iris Rivero is the Paul and Heidi Brown Preeminent Chair and the Department Chair of IC at the University of Florida. She received her Bachelor of Science, MS, and Ph.D. in Industrial and Manufacturing Engineering from Penn State University. Her research group, Interdisciplinary Manufacturing Engineering and Design, iMED, laboratory, specialized in design and validation of additive and hybrid manufacturing techniques for the processing of a wide array of material systems, ranging from biopolymers, metal alloys, to concrete. She was a faculty fellow at NASA's Marshall Space Flight Center, and her research has been funded by NISF, DOE, and NASA, to name a few. She has over 90 peer-reviewed publications and over 100 invited talks and peer-reviewed presentations. She's a fellow in the IIC and in SME. Okay, without further ado, let's give the stage to Dr. Rivero.
Thank you, and thank you for hosting me. Thank you for the great introduction too. I've been told that I have exactly the time right there, so I'm going to jump right on the presentation. I had somebody that came here and asked me about, I'm curious about why are you looking into large-scale 3D printing, and I made sure that that is right there. I'll let you know. But let me start a little bit about UF, Industrial Systems, what we look like today. You see, this is all faculty here. The one in red is one of your own from Wisconsin-Madison, so it's Dr. Minhee Kim. So we're really proud of her and the product from Wisconsin. That's why I wanted to highlight her there. She's going to hate this, that I did this. Oh, no, I'm going to have to highlight her too. Okay, no, so I didn't realize that completely. And so Chan is also there. My other people that are in orange, those are our career awardees. A couple of people asked me today about where are the areas in which we're actually specializing. Those are going to be advanced manufacturing, data analytics, operations research, and human system. Although I have to stress that our operations research is truly one of the largest part of the whole department. Which brings me about what are we doing in the expansion of smart manufacturing. It's just bringing the core of OR and optimization right into manufacturing processes for a lot of controls, in situ control processes and modeling on it. With that said, we're growing our facilities, so we're having a lot of additive manufacturing, traditional LPBF, traditional DD, but we're expanding into what we're going to talk about today a little bit. And we also have a driving simulator that I talked with somebody today about it with 6-axis motion. Is there. And materials characterization. One thing that I wanted to bring for collaborations is that we do have the Hypergator supercomputer. It's there. It's open for collaborations. There's time that is that is available. So if you think about anything that you would like to use, I know NVIDIA just upgraded again the system, so it's available for any collaborations on it. But with that said, let me start a presentation about motivation for what we're going to talk about today. And I update this slide every so often because the amount of printed nozzle tips that happen keeps growing up and growing up. So when we started to do research in the area of either 3D printing or prototyping or now additive, there was a lot of emphasis on taking prototypes into production. We did a really good job with that. Last few decades, we've been able to do parts that actually go into production. Lots of those are going into aerospace, and lots of it goes into defense, and a lot of it goes into medical applications. And I put always the example of Invisalign because it's one of the easiest ways to actually visualize how well we are actually using 3D printing in a production setting with Invisalign production on it. Polymers-wise, we're very well established in many ways, depending on what you're doing, depending on the material, so I'll be careful with that. But we see like here and there types of applications where you can incorporate 3D printing in an efficient, economical way that makes sense. And I think in my thoughts in thinking about why that's the case, why we have not seen a wide expansion of 3D printing in the production facility, to me comes down to that quality control. Can we actually do this product? Could it be repeatable? Could it be with precision? The application that could actually afford it would be also part of it. We still have issues with production rates, and I put it in gray there because I'm not going to dive into that because that's a subject in itself on it. But why production rates when you can actually be doing multiple parts, and with rapid printing or rapid prototyping, it does take time. So those are some of the aspects that I do envision are part of the reason why we have not seen integration into production settings. When I talk about quality control, I'm going to be talking about how do you make sure that the process is repeatable in the traditional parametric way with process parameters being controlled and being able to get the same quality one part after the other. And specifically in two main areas, in remanufacturing or repairs. So remanufacturing or repairs are something that is really picking up quite a bit in the way that you can actually reuse those materials in the most efficient way, and in infrastructure on it. So those are the two main applications that I see could have a value for being able to be integrated into production settings on it. And when I look into that, the way that I envision that could work into the large scale, especially for infrastructure, is that it requires a lot of different fields to go into it. It's definitely interdisciplinary. You'll need people in materials, you need people in computer sciences, you need people in manufacturing, and AI and ML, and working together towards that goal is actually a good problem, but it's not an easy one to actually attack. With that said, let me start with an example of one of the large-scale 3D printing applications to think about. So when you look at this EPA graph that you see here, what you're going to be seeing is that most of the green gas emissions are coming from the use of iron and steel. It's about, like I mentioned, there's about 29.7% with the last EPA that was published in 2017. And so that is a major issue that we're having. And we actually, if we scrap something and remake it again, we're contributing to actually those green gas houses on it. And so if we actually think about how can we use, instead of scrapping those large components, how can we reuse them in a way that you bring back their utilization to almost the same as when it was brand new. And in that way, we also contribute to then reducing the use of energy and the amount of emissions that we actually are contributing to. So when I'm thinking about large-scale components, I'm thinking about John Deere, for example. If you have an engine block on it that, you know, this is meant to last for a long time, and they do last on it. So it could be an 80-year-old engine block. There's no blueprint for it, or there's no designs for it. There's nothing that could be available. And all it needs would be repairs for cracks on it. So how can we actually use the similar materials and get the same level of quality from one repair to the next repair to the next repair? There's a high level of uncertainty because you don't know what the repair will look like. You don't know the material that you'll use. You don't know the parameters that you need to be using to be able to have a repeatable quality control process on it. But at the same time, if you actually scrap that and put it back into remelt, the amount of emissions that you're going to be contributing is significant. Not to even mention that still production in terms of cost is still going to be much higher than doing a repair for a component like this one. Same thing happened with any of the engine components, not the actual frame of airplanes, for example, but engine components is another area where you can actually see that you can use just a certain amount of material and repair the pitting that does happen, especially in rotational components. It's something that efficiently is more economical, is possible. Sounds easy, but it's not. It's actually not trivial whatsoever. So what we have been looking for a little while is using hybrid systems, and I mean hybrid systems is using both, not just additive direct energy deposition, but also using machining operations. This would allow you to be able to do the transition a little bit easier into a production setting in terms of the workforce development already is used to use in CNC, of course. And all that you're going to be adding is a miscellaneous code to be able to do the repairs in terms of workforce development. Now, when it comes to the actual repair itself, what you're going to be noticing is that you're going to be generating less residual stresses. You have a very localized source of heat going into that area. When you look at the interface between the substrate and the actual deposition material, what you're going to be seeing is that there's going to be significantly less distortion. And when I mean distortion will be that heat affected zone is going to be very minimal in comparison to a traditional repair that will be using traditional wire arc welding. And so they can actually visualize it instead of me actually talking about it. You'll see it right there in the, let me see. Could probably put it here, yeah. You can see here, so traditional repairs will use just welding. So this is a thick repair, and that's the heat affected zone. You can see how large that is. Of course, we know that that's the source where you're going to have the most fractures. It's going to be the weak point of your overall repair. But when you look at a DED heat affected zone, you can see that it's very thin. And it does allow you to have, it's also more controllable if you actually see it, how it is the same width throughout the whole repair. And when you actually look at the stresses too, you're going to see that the stresses are going to be more associated with pockets in certain areas instead of distributed all throughout in the tensile region. So there are some reasons to be able to consider that. And so with that said, I'm putting that into your mind with the ability to be able to restore to original properties. Here's some of the areas where you can see that are needed still to be able to do repairs at that large scale on it. So I put here cast iron. If you have worked with cast iron, it's horrible. It's just very difficult to work with. Nothing really sticks to it very well, but it's very durable on it. So to be able to do cast iron repairs, it's going to be very difficult to understand what are the aspects that need to be quantified to have a surface integrity that is the associated one to provide you with 90% of the fatigue life of that component, for example. That correlation between the process parameters is not really out there. Like I mentioned, with repairs, the difficulty is that you have an uncontrollable type of initial setting. So to be able to have those parameters completely correlated is a little bit difficult on it. And so you have to be almost on the fly. And then the other aspect that is important, if you're going to be using stainless steel, it's very difficult to control temperatures associated with the bonding in between those two materials on it. So if you think about that, and we were talking about, okay, so those are the problems, and we're going to have so much uncertainty. So what can we actually do to be able to do that? So the holy grail for all of this would be to have sensors that are allowing you to collect the data of this information right on the spot. And it would be a closed loop system, and you can actually correct on the fly. That's the holy grail. We're not there though. And this is where bringing all of the different areas in our field of industrial and systems engineering becomes extremely crucial to be able to integrate this kind of large-scale component repairs into a production setting. I mean, don't get me wrong. I think that in the future, and this is already, Medusa is a project that you probably know from the Oak Ridge National Labs. And you can see that in the future, what we want to be able to do is not only build up, but use this kind of technology with embedded sensing to provide live feedback closed loop systems on it. Ideally, you can also do your modeling. You know, and you can actually model what the expected conditions are going to be there. For example, if I use this hit input or this particular velocity, I could create a machine learning model to be able to do a prediction on how any different types of defects or different cracks are going to be behaving. So those are some examples. But before we actually could integrate this into a production environment or into any kind of repair situation, we're going to start in the very, very, very small scale. And you can see that this is a smaller scale type of of project that we did, and it was with gray cast iron. You'll see that we are able to take a look at a couple of things. So we did gray cast iron with stainless steel. We simulated a repair by basically creating a slot that you see here on A, and then we filled the slot. So in the middle of your tensile bar, you'll have the repair right there in the middle. And the idea was to start to unveil the different aspects that are going to be affecting that repair. So the main things that were affected were power, speed, step over, and the layer height on it. I mentioned that temperature control is really difficult. So we were trying to figure out ways that we can do in situ heat treatment as we're actually doing the operation to be able to control that bonding aspect associated with it. And so some of the aspects that you're going to be seeing here is that in terms of stresses, and we're talking about stresses, you actually get pretty good tensile stresses. And when I say pretty good, it's because they're in the lower area of tensile stresses. They're not compressive. That will be the holy grail there too. But when you look at machining stresses, are going to be significantly higher. So by understanding both of those sets of parameters that we get in this particular repair, we now could, for example, if you see that you're doing a printed surface that is going to provide you a tensile residual stress of positive 150, for example, of megapascal, you can actually know that you can change the power input. And that power input would actually then reduce that tensile stress on it. So that will be part of what will go into your closed loop mechanism. In terms of the bond strength, a couple of things that you're going to be seeing here is that speed is going to be a major contributor for the integrity of that strength. And in terms of whether that particular heat treatment made a significant difference or not on the repair, nothing really large or nothing really conclusive came out of that aspect. Primarily it was the speed temperature control. They provided something, but not as much as we expected with the heat treatment operation. And so right now what we have is of the things that we actually, the different parameters that we were controlling, speed and power had a contribution in the bond strength and fatigue life of that repair. And I mentioned that heat affected zone because that's what we're going to be focusing primarily on, how much you can actually control that. And you can see that in this particular graph, when you have different speeds, you can see that heat affected zone again, and you can see how it actually has a big impact, one, in the amount of porosity that you have in that interface, and the second one is going to be on how control that band of heat affected zone is in comparison to the lower speeds associated with it. You can see that just the lower speeds are just an opportunity to be able to trap air, and then you get porosity in it. So if you hone in even further that speed, with and without that temperature control, you can see that in terms of that the heat treatment, we can see a whole lot of changes in it. But with the temperature control, you do get less porosity. So, and this is a good example where you can actually see the amount of porosity that you're getting, especially when you're doing something with temperature control and without temperature control. So I thought, whoops, that's not it. Okay. Okay. Well, I'll continue on that one. Why did we see that porosity? So I have a few videos here to show you. And what you're going to be noticing is that when you actually change the speed, you can see that in this melt pool situation, the higher you go in speed, and these are basically without heat treatment, you can see a more stable melt pool, having less satellites just going throughout. And with the very, very slower type of melt pool, what you're seeing there is just a lot of bubbling. There's a lot of gas escaping from the melt pool, and there's other ones that are getting trapped, and they're getting larger porosity associated with it. Couple of things there too. This is basically running it at high wattage too. So that's important as a parameter too to understand. Let's see. All right. So couple more of these videos. So if I go at a lower wattage on it, and so you're going to be seeing that it's there's a decrease for sure in some of the amount of satellites that you're actually getting there, and you're not seeing that same big opening of the melpole and then getting smaller and large and smaller. And so what you're going to be seeing here is that the most particular case, there's going to be a increase in that dilution in between the two surfaces on it, and that's with the reduced amount of the wattage on it. So in a very, very, very concise way, couple of things that came out. Cast iron is extremely difficult. It has a very high carbon content within. It's a great precipitation of trapped gases too that create those voids. You definitely want to be thinking about preheating, but also annealing after your repair to be able to get to the levels of strength that you require for it. It is definitely a feasible technology, DED, for restoring mechanical strength. So it's something to be considered, but in terms of opportunities of what's the future to be able to get into repairs of large components is that even though we have a very general idea of how porosity is formed, we don't really know the exact mechanism associated with that porosity formation. And there's very different aspects associated with what parameters are associated with particular behaviors that we are getting in repairs on it. And the more important part is what kind of in situ monitoring system we can actually install for it to be able to understand those. And we are in that phase. In fact, I work with one of your colleagues right here. This is some of the work that we have been doing together and being able to have in situ sensing using scanning, computer vision to be able to identify when the porosity is going to be occurring and being able to change the parameters and then decrease some of the amount of porosity that we see. So in terms of where other types of opportunities could come, I mentioned in situ sensing, but the more important part would be data fusion and then data integration in machine learning to be able to control the overall process on it. And so that's an opportunity in terms of the sensing and understanding what we're actually getting out of the process. Other opportunities that you can see are using in situ imaging, so using Schlieren imaging, for example. Why would we want to be looking at something along this ways is because when you're doing this type of repairs, you're going to be controlling the environment to be able to reduce the amount of porosity by basically shooting a lot of argon on it so that you have a very controlled environment there. The turbulence in which you're introducing your the gases that are going to be maintaining a stable area are going to be changing the way of the bonding occurs. So when you look here, you're going to be seeing the Schlieren mechanism. So a couple of pictures that you see on your left, you're going to be seeing how turbulent that chilled-in gas flow is. And on the right side, you're going to be seeing that CT scan of that repair and how the initiation of some of the porosity is occurring on it. And so being able to model and being able to get this into a closed-loop mechanism will really get us out there to be able to do these repairs with repeatability associated with it. So those are some potential opportunities that we can actually see in terms of getting the process going into production too. So a couple of things from this study, very general. So this one is primarily, we want to be able to quantify this. The suggestion from the CT scan that you see on the right, you're going to be seeing that if you go fast or if you go slow, there's going to be different types of inclusions that are going to be introduced into that particular repair on it. And so controlling how turbulent that gas mixture is going to be important for that surface integrity repair in the bonding region. So that's a little bit on the area of metals, and that's more in the aerospace area. You can probably see agricultural area where we can actually make an impact for repairs. If we move to another area, I call it AIM, which is additive infrastructure manufacturing. And so the idea behind this is to be able to use a sustainable infrastructure. And what I mean by a sustainable infrastructure is that supply chain of a lot of the materials for infrastructure are in a delay. They're completely delayed, so it takes longer for construction projects to be finalized, and it's very expensive on it. So it's sometimes more expensive than even some of the aerospace facilities on it. So can we actually understand the ecosystem of the region and then introduce it into the process to be able to do accelerated infrastructure, whether it's from the ground up or whether it's for repair, either one of those. There's a few things that are going to go into this. So we do have a program that is in the process of approval. It's called Industrialized Construction Engineering, and it's a multidisciplinary effort between the Design, Planning and Construction College and the College of Engineering, with 2 departments leading industrial and systems and civil engineering. And what we're doing in that industrialized construction area is how can we use smart manufacturing and structures and Industry 4.0 to be able to develop a solid structural health monitoring to be able to do more precise type of infrastructure and also workforce development. So, and I mentioned workforce development, even though it's not the technical part of it, because the construction industry has seen a significant reduction in workforce available. And this is a means to be able to energize that particular sector as well. So this one is going to go into it. So this is our new baby. This is going to take me to another screen, hopefully. Yes, okay. And you can, as I talk here, there's nothing spectacular in terms that it's just moving. So this is our new system that is able to do pretty large constructions. And you can see here a couple of things. We are very interested in that interface where you have your nozzle and you're doing deposition. You can see so many defects happening. Controllable parameters are very difficult. This is one where the environment plays a big role on it to be able to have the mixture associated that gives you the viscosity necessary to do multiple layers associated with it. So lots of opportunities to be able to do, for example, lighter type of assessment in a layer by layer situation, and then do prediction of cracking. So what we're printing here that is different from other types of printers is that we're printing basically a composite where we do have, this is concrete with aggregates. So your aggregates are going to be influential in the amount of porosity that you're going to be getting, and also the stress points where you're going to be seeing some of the issues associated with crack propagation in vertical type of structures on it. You see this is an effort that does require people from multiple fields to come together to be able to do the process. But if we're able to provide information about what is happening at the layer by layer deposition of very large structures, we're going to be able to really make an impact in the construction industry. So I'll take you out of this mesmerizing view. My students always just put this on the background and they like to see it. And take you to where do we see a future? So it's going to be really interesting. So there are efforts out there. So you may have heard of a place in West Texas, it's Marfa. It's a very artistic type of community, but they're trying a new project, and they had a hotel there that was primarily bands on it. It was just different RVs together, and those were the rooms. So they actually closed that. That's the old El Cosmico, and now they're doing the new El Cosmico that opens, like I said, there in 2027, and it's going to be basically one of the first full-blown hotels that is 3D printed, and it also has a high-end community too that is being offered. The magnitude of this is that you can actually do this fairly quickly. And just to put it in perspective, so they did started construction in 24, and they actually are planning to open in 27. That's a big deal. That's definitely a big deal, because what you're seeing that they're going to be doing is 43 units for the hotel, 18 homes, that's in 60 acres. And the main aspect associated with it is that if you actually do that with traditional type of construction, you're going to be looking at significant length of time, and you're cutting it here to like 20% of the amount of time that would require for that large type of aspect. So about 70% time reduction on it, 70 to 80. The other part too is that you're using only the materials that you need to be using for the construction part instead of actually using concrete. We all know concrete is not great for the environment either. So you're able to really restrict it to the amount of material that you need. The other part is too that there are a lot of accidents. So if you're in safety and human factors, there's about 10 cases of 10 workers that get injured during each year in each of those construction projects on average. So you can significantly reduce the amount of safety aspects related to construction. And so so this is a very, very big deal because a hotel of this magnitude would have taken years. It could be even 10 years on it. So that's where we see some future associated with it and the speed up. But if you're thinking too about other type of repairs, if you have ever been in a concrete place that looks like this, there are some colleagues that are working in this area. And so you can do infrastructures in the vertical, but also horizontal. So for example, when you look at the UK, they do have a particular vision for this, that by 2050, they're going to be able to have what they call the UK Self-Repairing Cities Project. And what that means is that they're going to be able to fix all of the routes without minimum interruption on it. The constraint that you see here, it's not a constraint, but they're primarily just repairing with asphalt, not a lot with concrete, and it's using drones. And there's many aspects associated with it that are technically challenging. But the good thing about those technically challenged type of issues is that it open opportunities for research for us to be able to do. So what do we see in terms of it? You can see that it all relies a lot on that sensing aspect and the integration of different technologies into one. What do we need to be able to get into having this type of projects really go out there and that you see more 3D printing structures is one, the ACI code for construction is not yet defined for infrastructure on it. That's going to be one. So you have to make sure that you find the engineer that is going to sign off on the structural soundness of that. Materials on it. So if you want to be using local materials, you really have to understand how they're going to behave in this particular type of new process with it. Concrete reinforcement, so like I said, a lot of printing happens with mortar, which is fine, it's very smooth, it's fairly reliable, but in terms of the usage of that, it's going to be limited in terms of time. And that could work for certain industries. So for example, many companies that want to build distribution centers very quickly, and they're only going to use it for a little bit, construction of 3D printers with mortar that lasts 7 to 15 years is fine, because they're not going to use that distribution center for long on it. But if you're thinking about something that you need it to last, you have to start thinking about how come you actually use move region mortar. There is not a whole lot in the specs for QA and QC, especially in civil engineering when it comes to 3D printing. So there's an area there for data analytics that could be extremely useful. And like I mentioned, there's not a lot of regulation right now for it. So bringing something that I'm working with colleagues right there in Iowa State still. It's a sample project, and we're trying to use local supply of materials. And so with this one, what we're going to be using is, you probably know in Iowa, and here too in Wisconsin, there is a lot of turbines on it, so wind turbine blades. And what happens is that they get decommissioned, and they send them a bunch around, including a whole facility in Iowa State. And it's full of carbon fibers of decommissioned turbine blades on it. So we were thinking, how can we actually use that to our advantage instead of just being this big place full of this? So we started thinking, can the reinforcement on the concrete, moving away from aggregates, could it be this carbon fibers that came from those wind turbines? blades. And we started thinking about that it is not new in civil engineering. They've been using fibers. They've been using carbon fibers. And I put there some of the examples. They're carbon fibers, glass fibers. And in their world, for them, it really helps them because if they have a crack, having that reinforcement then basically stops the crack from propagating on it. Which in the mechanical world and industrial world, we know this in the composites type of world altogether. In the civil engineering world, they struggle with the soundness of all of this type of composites aspect. But if you notice from this picture here, and if you're looking at the aggregates and the crack formation in comparison to fibers, it's going to be kind of very important to have some control on the directionality of the fiber to be able to restrain that crack formation. So what we started looking into it is doing the customizing of the nozzle to be able to introduce those fibers into it and seeing whether we can actually affect the directionality and be able to get the strength associated with that reinforcement. And could it be actually comparable to your traditionally masonry on it? So masonry is out there, and they do use composites, but how does it compare to a 3D printed with already used type of supply chain? Very local supply chain, I must say. So what happens? You probably saw that the problem with this is going to be that we're going to have the issue that those fibers are also going to be the problem for the nozzle getting clogged up on it. So it's going to be an issue too. So how do we actually control both the strength, because we're going to need a certain level of fibers into the mixture, and we also don't want to stop the process to just clean the nozzle every single time. And also we want to be knowing so whether we can actually get some directionality. So what you can see here is that there is a region that, of course, depending on the size of the fibers, you're not going to be able to print much, and have it categorized there by the fiber diameter. And so if you're going to be in the larger region, you're going to see a lot of clogging. That sweet spot there with a C for number 16 seemed to provide us like the better outcomes when it came to printing, and the length as well was important to be able to do that. So 16 was one of the better ones. Fiber content as well was all the way to 1%, 2%, and we were able to do that. And I'll show you in the next slide what it will be looking like. And so for you can see how the samples that we actually were able to generate from it in terms of what we measure. So a couple of things that we were measuring were flexural stress and the flexural modulus. And the different categories that you're seeing here is basically the diameter of those fibers. And remember, these are batches that come in a bag. We don't have a whole lot of control for them. We're just putting them first without doing any milling, any ball milling or anything, just to see what we're actually getting. So you get an average of what the of some of them would actually have larger diameter ones, and other ones would be longer on it. And you can see, of course, that we're going to be seeing with the higher amount of fibers, we're going to get a better modulus related to it. And one thing with concrete is that it introduces a new variable, and the new variable with it is going to be that it does not really complete its process of solidification until 83 days. So the result that you're going to get in 7 days could vary drastically in 28 days or 50 days on it to be able to accomplish what you're trying to do. So there's an aspect of prediction based on the parameters or the properties that you see at the start of your print, and at 7 days, 30 days, 50 days, to be able to predict whether that's going to be a solid structure, a structural sound type of structure. So after 28 days, you can see that here when we're varying that particular diameter, the better one is not, it is still in the number 16, you have a little bit more flexibility with the 30. At 28 days, there's dramatic difference too when it comes to the fractional stress there. It's still a favoritism for the number 6's diameter on it, but you can see that it's a radical difference in terms of the other behaviors of the other diameters of fibers related to it. The graph at the bottom shows you some of the aspects related to traditional masonry, and this is why you do want to make the comparison, because sometimes, depending on what you're creating, maybe traditional masonry or maybe a hybrid of traditional masonry and 3D printing could provide you with the better fatigue strength of that structure. So with the number 16, what you're seeing is that there is some improvement on the modulus on it. But in comparison to your traditional cassette masonry, there is a difference. It's not a significant difference on it, but there is a difference associated with it. Again, that's only 28 days cast. So to get to 80, we still are in the middle of doing some of this, the testing associated with it. So I'll be leaving it kind of in a cliff here for you to learn what happened at 80 or 83 days. Couple of things that were important here. The nozzle effect, we work with a few things. Of course, when you look at this, you're like, oh yeah, if you taper it to a certain level, you're going to get some directionality, better control. And yes, that's true. But I also want to have a higher production rate. And so we really wanted to fine tune between higher production rate with a larger nozzle. Also will help with less clogging. But you have not a whole lot of control with the directionality of those fibers, and then that really impacted our flexural strength and compression strength associated with it. So it was an interplay between those two parameters that are important on it, trying to work with the production rate and trying to also get to the levels of strength that we were looking into. So, but you can see there that some of the comparisons that were done, and there's still a work in progress on it, in a good way. So, definitely a good way. And so what are the things that are opportunities here is going to be that if we are able to use that example of fibers, and especially fibers from the environment that are present in the area, is it possible to make sound structures, infrastructures? We want to understand also more about if we can control the fiber, especially the length of the fiber, if we actually are able to have the same length throughout, what kind of improvements we're going to be getting in quantifiable ways. And of course, the nozzle size is going to be important because it's always going to be an interplay with production rate to be able to have a faster or distribution of how long it takes in that construction site will be important. If you don't get the 70% to 80% gain of your construction time being reduced, then it makes more sense to stay with traditional methods on it. So it's important to actually address the aspect of production rates. And opportunities, I always see the in situ process characterization, data acquisition, process modeling is not there yet. So those are virgin topics to look into. We also want to be trying to go from that low TRL level to be able to be used and have industry engagement in the construction area is not there yet. And I'll leave you with a little bit of nuggets to think about other aspects that you can actually use, basically AI-infused smart manufacturing. So if you think about, I call it infrastructure 5.0 in smart manufacturing. Some of the issues that we have with infrastructure 5.0 is going to be the scalability and the reliability of those large components. So if we're able to think about all the different parts that are going to go into being able to have a reliable, scalable type of operation in infrastructure, you're going to be really trying to get data right there, real time, so you're able to make the decisions and change the parameters on it. So what are some of the areas that are of interest for my group at UF and myself? And it's going to be aspects associated around digital twinning on it. It's going to be less expensive than actually doing these structures. You still need the qualifying elements. You still have to do that to be able to get ACI compliance. But digital twinning will be a method to do, to go work. We want to work too on sensor design systems and then that real-time control along with the workforce development and training on it. So lots of opportunities in industrial and systems engineering to make a really big splash in this intersection between industrial engineering and civil engineering and architecture. And with that said, These are the people that are there. And so we had a big ribbon cutting ceremony. And so those are the students and the postdoc and everyone. And I wanted to thank pretty much my team still that we are working together at Iowa State. My former student, Jacob Hamilton, became, I'd like to say like a mini Iris there, but he's 6'3", so it's a very different Iris altogether. I wanted to make sure that I had enough time for questions and also to brainstorm, so please, I welcome those. Thank you.
Any questions from the audience?
Yeah, thanks, Iris, for this very inspiring talk. Yeah, I have a clarification question on slides 27.
Yeah.
Yeah. So I'm curious about the video sequence from the CT scan, from the X-ray. Yeah.
This would be easier to go this way.
Yeah. 27. Yeah, this one.
Got it.
Yeah. So for the porosity image,
Yeah.
the video sequence is from a time or from the different location, like from the space.
Yeah. Yeah, are you talking about the CT scan? How is it? Is the region that we're seeing here, is that one? And
Yeah, I'm showing, we see the porosity, like for the bigger image, we see blue, those porosity location.
Yes.
So this sequence is collected over time or collected over the different location in
different layers, yeah.
Different layers.
Different layers,
okay.
yeah. No, definitely.
Okay.
And the difference here was the scanning, the speed of the deposition on it. And you can see one is going to be providing larger porosity on it. The slower you go, the more time you have to trap the air on it.
So this sequence you obtained is after the whole workpiece is finished.
Yes.
Then you just polish it, get one layer off to do it. Okay.
Yeah, so if we can actually do this at the same time, that will be the case. And you know what Hantang is doing here with computer vision is attempting to do that too. That this was installed in the system that we have both at RIT and the system that we had at Iowa State. So that computer vision was right there as we were actually doing the deposition on it. That's what we would like to do to be able to then just eliminate some of those spots if we are able to know that that's what's going to give us with certain parameters on it.
So have you seen a case like the repaired workpiece actually is stronger than the new one?
Yeah. So I was talking about this one with the bond strength, and I went through it very, very, very quickly.
Okay.
But what you're seeing here is this, the original one is this one, and that's just a traditional gray cast iron engine block. One that was introduced with some cracking. If you notice here, when we did the faster speed and we did localized temperature control, you can get even better service life out of it, for sure, yeah.
Okay,
But
thank you.
Yeah, no, thank you for the question, too.
Thank you.
Other questions? Okay, so probably.
The pretty picture.
Yeah, very nice talk. And the concrete 3D printing video is very cool. And
thank you.
Yeah, and I noticed that when the printing of concrete happens, it has some satellites from nozzles. Yeah, I do research about the electrohydrodynamic printing, so I know that such satellites are very normal.
Yeah.
And I see like a lot of people like when they see the satellites, they want to arrange this kind of satellites or extra printing. So I want to know that what will this kind of satellites influence the concrete printing and also even the construction of the 3D printing for the houses?
Yeah, I think that's a great question. I like that question. I think I'm talking with one of our colleagues in civil engineering to be able to use an ultrasound system to be able to at least learn when those satellites are occurring and then slow down the process or speed up the process. We haven't installed it yet, but we have the mechanism already to go right in that nozzle location to be able to do that. We're going to have some issues because that is great for the lab, but as you may know, ultrasound is going to be affected by anything around it, any kind of vibrations, any kind of like sound. So what that's going to allow us to do is understand the process and then think about what other NDE techniques we can actually use to be able to understand when we're going to get those satellites and how to control them on it. But the first step that we're going to be using is ultrasound right at the location. Yeah, no, that's a great question.
Yes, thank you.
Mm-hmm. Of course, LiDAR is another one, but it's not as precise in terms of information for it.
Okay. Would you like to ask a question?
Thank you for this very interesting talk. So I have a question regarding the carbon fiber reinforced concrete. That's one. So I just wonder, we already know that by any fibers, the performance of the concrete can be reinforced. But I mean that for the microstructures, there must be some so. Actually, do you have any chances to investigate how the microstructures of those fibers in the concrete to influence on the performance? Actually, the microstructure to the property, this relationship. Yeah, did you get a chance to investigate it? Yeah,
not other than traditional disc ones, like stress, modulus, and compression. My colleague at Iowa State, he does structural health monitoring, and the next step that we're going to do is adding some of the sensors to be able to look at the microstructure and correlate it to the overall curing time of it, but not quite yet on it. Yeah, so far it's been the traditional methods just to be able to validate how strong, what forces, and where the cracks are going to be occurring.
Thank you.
Mm-hmm.
Yeah, I also have a question.
Yeah.
So for this, your first topic of DED, in this kind of process, we have basically two types of measurements. One type is very hard to acquire. For example, this microscopic, image and also X-ray CT. But typically in a real manufacturing process, we are only able to get this kind of, this in situ image sequence.
Yeah.
So one question is that when I talk to these manufacturers, they typically manufacturing researchers, they typically very like the first type of measurements. However, in real time, it's hard to integrate these type of measurements into the real-time analytical framework, to do this real-time quality control. So do you think there are some, formal way of integrating this knowledge, the data of these kind of offline, expensive, testing into this, the model, instead of just, review the mechanism and put this data aside?
Yeah, I think that the best way to do that, to be honest, the mechanisms that we have to work with industry are going to be important. Right now, we're working with a company, Hybrid Manufacturing Technologies, and we're working on how can we actually incorporate in situ 3 different types of ways of measuring. Of course, all has to be non-destructive testing if you have it in situ. So I think having OEMs that are able to partner with academia, de-risk, and basically show and tell, I think that's going to be a big step towards getting this kind of inspections, in situ inspections into place on it. But I think that it's going to be at the tandem work. If we continue only academia in one space and industry another one, we're still going to be at that tier level of 2 and 3, not bridge it on it. So I think it's very important to identify those OEMs that are willing to partner to explore these alternatives. Mm-hmm. I'm not saying traditionally to just get funding from them, but more partner with them in securing funds in other ways to be able to just further technologies together. And then that provides basically a de-risking, because most companies don't want to have the risk of installing something extremely expensive that may not work on it.
Yeah, that's right.
Yeah, so it's a collaborative work for sure.
Yeah, thank you.
Mm-hmm. You had a question, Mike.
Are there questions?
Yeah, that's very interesting with the fibers. I was just thinking about the clogging issue.
Yeah.
I mean, once they add additives to my thing, they also clog. But I'm wondering if there are ways to put an ultrasound or a vibration system inside of the vessel, so it kind of,
Yeah.
get some excitation to kind of mix it up better once it exits.
I think that'll be, it's funny that you said that because I was in between two different types of projects, and one of them we are vibrating, but we're using some wiring to be able to mix it. And we're getting good results. We're getting really good results associated with it. I just kind of was like, which of these projects so it's very funny that you mentioned that. Yes, I think that is the way to actually do it. And it's better than any other techniques. Sometimes people think about shaking the table or shaking something, but that doesn't make sense in a real world. So, and instead of vibrating the nozzle, then we install basically a mechanism that could actually shake it there. Great idea. Yeah, great idea. Mm-hmm.
More questions? Okay,
I was
thank
going to
you.
say, and if you think about ways that you want to collaborate, we're always looking for collaborators. Thank you. Thank you. Goodness. Let me see.